Hello and welcome back. Alright, so in our last example, we went back to calculus, single variable calculus, to find the area under a curve. And it was pretty easy to do, but now let's take a look at how we would do that using double integrals in multivariable setting. So now let us write a double integral that calculates the same area. In this case, we're going to use both in the xy coordinates to create a two-dimensional area and summing up the amounts to calculate the area and volume. Alright, so we're going to get the same basic answer right here. So the first thing we're going to do is we're going to talk about the vertical rectangles. Now we talked about this before. In the vertical rectangle, if I draw me a vertical rectangle right here, we are going to be in terms of x. So in terms of x, this is going to give me my change. So this is going to be in terms of my function will be in terms of x. So we're going to have our function, our value right here. If we look right here at the very top, this is going to give me my maximum y value, and this is going to give me my minimum y value. So that kind of gives me the range. So because we're in terms of x, that also means we always do the vertical first. That's why I start with the vertical rectangle right here. So that's going to give me my change in my y values. Well, what's the smallest my y value is going to be? Well, that's down here at 0. Well, what's the largest my y value is? Now remember, we're in terms of x here. So the biggest my y value is f of x, the function itself. Now I actually know what that is, so my y values are going to go from 0 all the way to the square root of x. So that's going to give me my change in my y values right there. Next, if I look at the horizontal part of it, from 1 to 4, right, there we go. Here is my minimum x, and here is my maximum x. So I can get my change in my x value. So what's my smallest x value? What's my smallest that x can be? Well, the smallest x can be, of course, is 1. The largest my x value will ever be is 4. So as I'm moving this one up and down, the smallest it's ever going to be is 1, and the biggest it's going to be is 4. So when I set up my integral right here, when I set it up, I look at the intersection of my horizontal and my vertical rectangles. And we want this little tiny piece right here. And remember, we said the area in here is just dy, dx. Now the reason why we do dy is because our function was in terms of x. Remember, we were looking at the function y equals the square root of x. Because we're in terms of x, we're going to choose dy first. So this is saying that y has to go first. So I set up my area problem. My area is a double integral because I'm using both parts, my vertical and my horizontal, and it's going to be dy dx. Well, so I work with my inside function first, so I ignore that. So I ignore those. I look at the change in y. Well, my y is going from 0 to the square root of x. And then my x's are going to go from 1 to 4. And that would be our setup. Well, let's go ahead and solve this, okay? If we were to solve this, looking from yesterday, we would integrate the inside first right here. And if we integrate just the inside, we're going to get y from 0 to the square root of x, which of course is just the square root of x. So my new integral from 1 to 4 would be the square root of x dx. And if you notice, we get the exact same integral as we have over here. Okay, so we're going to wind up with the same answer right there. Now you might be thinking, oh my gosh, this is crazy. Why would I do this extra work? I promise, again, there is a reason for this method. We're going to talk about that later on. We're going to see some reasons today, but there is a reason we will like to write it like this. So let's try a couple more examples. Excuse me. We want to write and solve a double integral that will evaluate of a rectangle with x coordinates of a to b and y coordinates of c to d. So we want to find the area of a rectangle. So if I draw a rectangle, my x coordinate, so if I draw this in the xy coordinate plane, my x's go from a to b, and my y coordinates go from c to d. Well, if I draw my horizontal rectangle and my vertical rectangle, I'll use red. If I draw my vertical rectangle and my horizontal rectangles, right here, I am looking at, oh look, it's like the Swiss national flag. If we look at this tiny little rectangle right here, remember, this is going to be dx thick, dy wide. So, now, you have a choice. They don't tell me if it's in terms of x or y, so you have a choice. So, my verticals, remember my vertical is going to be my change in my, excuse me, whoops, can't spell vertical. Our vertical rectangle is going to give me the change in my y values. So the y values go from the low of c to the high of d. My horizontal rectangle, that's going to be my change in my x values. Well, my smallest x value is a, my largest is b. Now you can write it this way, or you can write delta y is from c to d, right? And delta x from a to b. You can write either way like that. So if I want to find the area of this rectangle now, and I'm going to choose y first, so dy dx, and I do my double integral. So if we do our double integral, the y's are going to go from c to d, and the x's are going to go from a to b. And if we were to integrate this, let's take a look at what happens if we were to integrate this. If we look at the inside, we're going to get y from c to d, which is just d minus c. And then I would integrate that from a to b, d minus c, dx, which just becomes x, d minus c, from a to b, which of course just becomes b minus a times d minus c. Is that kind of cool? Take a look at the area right here. How would I find the area? Oh yeah, it would be, I would take b minus a and multiply it by d minus c, and that would give me the area of my rectangle. So it's a really cool way to prove area of a rectangle right there if you want to take a look at that. Alright, for example number 3, let's take a look. We want to find the area bounded by the graphs of y equals sine of x and g of x equals cosine of x in the first quadrant. So the first thing we have to do is determine, of course, which quadrant, which is our shaded region here. And so we want the area bounded, so we're definitely looking at this region right in here. So we want to find that area of that little region. Now notice we are in terms of x. Okay, so if we're in terms of x, we are going to use dy dx, which means we're going to look at the vertical part first. So if I look at my vertical rectangle right here, if I look at only the vertical rectangle right here, I can get my change in my y values. Well, what's the smallest y value is going to be? This is my bottom, right, of my rectangle. And the bottom there is from the sine curve. The top function, there's my top right up here. So that is going to be our cosine curve. So I have my change in my y values. The horizontal rectangle, let's see here. There's my horizontal rectangle. Well, to get the horizontal rectangle, well, what's the smallest my horizontal rectangle is going to be? Well, it's going to start way down here at 0. So my change in x starts at 0 and goes all the way to, well, where do they meet? Remember, this is kind of a tricky one right here. So where do they meet? They meet at pi over 4. We know where they meet, where cosine sine meet. They meet at pi over 4. Oops, there we go. My pen's not writing very well. There we go. Pi over 4 root 2 over 2. So let's go ahead and find. So now we're going to get the domain for our horizontal. Of course, we're starting at 0. Well, what's the biggest our horizontal rectangle gets? It's pi over 4. And now I'm ready to go and set up my integral right now. Remember what we're looking for. We've got this little tiny little rectangle in there. Remember that rectangle is dx dy. So I can write the area as dy dx. Remember, we're going to do dy first because our function is going to be in terms of x. So we're going to use the dx first right here. So I could write this out as my area would equal the double integral dy dx. Now, dy is first, that's the inside, and that goes from sine of x to cosine of x. And my x's are going to go from 0 to pi over 4. And that will find it for us. So let's go ahead and evaluate this. It's good practice. If we integrate the inside first, we would get y from sine x to cosine of x, which becomes just cosine of x minus sine x. And then we would integrate that from 0 to pi over 4 with respect to x. Cosine of x minus sine of x dx, which becomes, let's see here, the antiderivative cosine is sine of x, and this becomes plus cosine of x from 0 to pi over 4, and that just becomes root 2 minus 1. Right there. You can verify that. All right. So going to video number 3, the next video, we'll take a look at another example. For example, what happens if we would have chose to do dx first? What if we did dx dy? There's a difference. We're going to talk about that in the next video.